Thank you, Lee, for your kind words. Indeed, I am a graduate of this university. I consider myself. When did I graduate? 2005, maybe? Or about, something like that. So I'm honored to be back as a student here. But what I would like to talk to you today about is something actually that doesn't have anything to do with the Nobel Prize. So it's something that my group have been involved with since the Nobel Prize. Because, you know, the sad part about the Nobel Prize is that when you receive it, everybody thinks that you're going to retire and enjoy going for dinners and invitations and giving lectures about the weather and everything else. But luckily, we stumbled on something that we are quite excited about. And that is the subject of today's lecture, 4D electron microscopy. I want to share with you the struggle we went through until it's amazing that in this department with lots of lasers,
there is a very small number.
Say something about the budget. Oh, I see. Okay. So, first I have to tell you that there's a very large number of people that have been involved since the beginning of this field, and we also have a center. You will hear their names as I go on. We have a recent center that we try to cross into areas from physics to chemistry to biology, and without really these colleagues, it would be impossible to be able to handle, as you'll see, cells and proteins and special materials. So I owe them a lot of debt here. So just briefly from a review I wrote recently, if we look at the history of structural determination, and especially in chemistry and physics, it began all around the beginning of the last century, and then physics had a heavy influence both for the development in X-ray and of the electron, and the chemists have picked up this, including Peter Debye, and it really both a combination of electron techniques as well as X-ray that brought about this revolutionary determination of big structures. For the student in the audience, we should realize that it all started with a 2-atom material, the table salt, sodium chloride. So if you can do structure now from sodium chloride all the way to a complex protein system, this is really an incredible achievement over 100 years or so. It's similar in terms of the, maybe I can turn this thing off here. No? Okay, maybe this way. So it's similar in dynamics. Actually, the first experiment with the hydrolysis of sucrose, which was taking seconds, and this was measured around the time that the famous Swedish Arrhenius, and these are all the Nobel Prizes that began with Van der Hoek, 1901, and continued on with developments until really the laser came on in the 1960s. This have created a whole revolution in terms of taking the time scales. It used to be here seconds, the best you can do milliseconds and the like, and laser really have transformed that completely, and femto, and as you know from Anne and other groups here now, we're crossing even this barrier. So what was important in those days, as you heard from Billy about femtochemistry, is that there was something fundamental, and we were lucky in a way, because the typical velocity at which the atoms are moving is about a kilometer per second, and the distance we are interested to see in separation is about an angstrom, and then therefore the time scale you are looking for is femtosecond. And essentially you can really go from kinetics into truly dynamics. That was the key. Here was always kinetics of ensembles. Now you can look at atoms during the course of a chemical or biological reaction. But up to that point, we did not know much about the spatial arrangement of the atoms in space, namely the structure. So we had no idea of how the atom, we can trap them in time and see what's happening, but we did. So I just want to take you through the struggle we had to do. It took 10 years actually to really get into where we are. And then once I tell you that, I'll tell you the most exciting things that we are seeing and working on right now. So very briefly, we began by ideas around 1997 of how to plot chemical reaction. But then we thought the first real serious paper that we could show that we can plot a structure of the chemical exchange in a molecular beam. And in retrospect, that was not too smart on our part because this is the most difficult experiment you can do. The molecules are isolated. There is no coherence between the molecules and themselves. And therefore, the signal here, it's impossible to observe it by any other means except by electrons. Simply because the cross-section here is so high, and this is you isolating a single isolated molecules in the beam. But nevertheless, we did this and we succeeded in trapping the structure for the first time of a chemical reaction going from ethane type molecules into ethylene type molecules. And we can now, for at least for us the first time, we can measure bond distances during the transition state of these chemical reactions. Before, we could measure the time, but we didn't know anything about this arrangement in space. And this, of course, was extended to many other chemical type of reactions. There is a recent review, Dr. Sharapov and myself, and we highlight some what we call ultra-fast electron diffraction. That means it's all an isolated system. There is no interaction between the atoms or molecules. And to do this, by the way, we had to develop something called the laser desorption. And in this method, the molecules, especially the biological ones, like peptides, I have an interest to ask the question, what is the meaning of hydrophobic interaction if there is no water around macromolecules? And so we built a special machine for this, and the idea here, we could not do it by the usual heating, so we had to use the laser desorption to do this. So you can see changes as such in ultra-fast diffraction. Then we got ambitious to go into crystallography. And there is a value in doing this because if we can do this, as many of the experts in the audience knows, you can get at surfaces and interfaces. So we created a chamber here, what's called surface type chamber, and then again we do diffraction by the same. And you can see here the electrons on those days, the best we could do was about 600 femtoseconds. And with these electrons shining on the material, we can actually obtain some valuable thing. This was published in 2007 about using electrons to look directly on the phase transitions of a material. And this was a commentary on this work here. So for example, you can look at an insulator transforming into a metal. You notice all these bonds here, they're broken, and when it gets broken, you form a metal. So it's a beautiful system in terms of understanding how chemical bonding in the material can influence a phase transition, a first order phase transition. So we looked at this through the diffraction, and a number of papers has been published on the subject. And in fact, you might be intrigued. Here now we are in the S space. This is not spectra now. This is the scattering vector. And this is one of the Bragg peaks for one phase. And then you can see it transforming in real time the structure itself, going into the other phase and returning back at longer time. And quite a very interesting story here, why a metal to insulate the transition take place in the femtosecond time scale, and then it recovers in the picosecond time scale. So I will not dwell too much on this, but just to, by way of review, this was the isolated system. This was doing crystallography, two-dimensional crystallography, but my dream always has been to get to microscopy. And the reason for that, if you look at Lund, Uppsala, anywhere, you will find that microscopy is in every department, essentially. From geology to biology, everybody uses electron microscopy. So the idea I had was simple. If we can indeed induce the time resolution, then we can add a fourth dimension into electron microscopy, and the techniques are unlimited, literally, as you will see, unlimited with this kind of techniques. So we tried this, and I just want to show you the where the time resolution was with electron microscopy. So this is seconds now. This is Professor Thomas speaking. Yeah, so they can see the reaction in real time. This is seconds now under the microscope. So, and you can go on to shorten the time scale. You can shorten the time scale. This was milliseconds. After that, it's all limited by the camera, video camera that you have on the microscope. And then in Germany, there was an attempt to do it with very intense nanosecond pulses. But it turns out you couldn't focus the microscope because the resolution was microns. So we decided to try to take this method, if we can really get it away from the typical video camera speed of milliseconds, and even if you get to microsecond, nanosecond, if we can open this whole domain here, then we will have both the picometer spatial resolution and the femtosecond, and you will see beyond in terms of the time resolution. That was the idea. So we thought, we are clever, so we thought to build about our idea of doing it, as I showed to you, with diffraction. So we took a microscope assembly, deassembled, and made some modification in it. And then we brought the laser machinery in order to create electron through the photoelectric effect. We bunch of electrons now are pulsed. There are lots of condenser and lenses and everything here. That this is just a schematic. And then we focus it on the specimen and we do this. I wrote this paper saying that this is the way to do microscopy, but it turns out to be the wrong extrapolation. Wrong because if the pulse has too many electrons in it, just like we used to do in diffraction, the electrons, not like photons, the electrons are charged. And so they repel each other, and because they repel each other, they end up defocusing by the time to get to the specimen, and worse yet, when they get to the detector. So the best time resolution we could see by doing it, even with an initial pulse of femtosecond and the intense one, we end up here with a resolution of submicrons. Now, for some of you who know about development in electron microscopy, you can see with electron microscopy the atom in real space, not by diffraction, in real space. So if you can image with this high resolution in the electron microscope, you should be able to see the atom. But if we're going to be submicrons, then there is no value in doing all of this. Well, it turns out that the idea, the reason it was not too good of an idea, is because of the fact of the so-called space charge effect. And Anne would know that in X-ray, you don't have this problem because it's light. There's no interaction. But of course, you don't have the strong interaction with the specimen. We have about 5 orders of magnitude stronger interaction with the specimen. So this is the space charge effect, which broadens the energy domain, and it caused the defocusing that I told you about.